Hi, hello. Let us discuss today one of the important concept in quantum mechanics, particle in a box. So let us take a situation that a particle is trapped in one-dimensional box in the x-axis, and this let us take a electron, a particle, and this is moving inside the box from x equal to 0 to x equal to L. So this particle cannot escape from the box because it is infinitely long. So the potential here is infinity. If you take the boundary condition, the potential of this is 0 inside the box between 0 and L, and it is infinity when x is at 0 or x is at L. So when it has reached here, it will have infinity potential, but inside it is having zero potential. Zero potential means the electron is moving in the form of wave, matter wave. So psi of x is not equal to 0 inside the box, but it is equal to 0 when it is at x equal to 0 or at x equal to L, because it can never be there, right? So it can be never be on the top of the box or outside the box. So psi of x is not equal to 0 inside, but psi of x is 0 outside, but it will never be there. The particle will never travel there. So let us see how to apply Schrodinger wave equation to this. So when we apply Schrodinger wave equation in one dimension, time independent wave equation. So d square psi of x by dx square plus 2m by h cut square, right? So E minus V of x psi of x equal to 0, but here V of x inside the box is 0, so we are going to write 2me by h cut square psi of x equal to 0. So this is our Schrodinger wave equation in one dimension, time independent wave equation. So here when we take this equation, there will be multiple solutions, but we'll be taking the solution which is satisfies this equation. So the solution that we are going to take here is psi of x is equal to a sine kappa x plus b cos kappa x. So you can differentiate a sine kappa x 2 times and substitute here, and it will satisfy the equation. You can take b cos kappa x 2 times, differentiate and substitute. It will also satisfy this equation, where this kappa we are taking as square root of 2me by h cut. So basically this is kappa square. So kappa is equal to square root of 2me by h cut. So if you take this solution and apply boundary condition x equal to 0, then what happens to psi of x? So psi of x, if you take, you know, sine 0 is 0, so this is 0, but cos 0 is not 0, so you will get b, which tells psi of x is not equal to 0, so it is not valid for this boundary condition. So at x equal to 0, psi of x is x equal to 0, psi of x should be 0, but it is coming as not equal to 0. So that's why this is not appropriate for this problem. So what is appropriate for this problem is psi of x is equal to a sine kappa x, this solution. But here also at x equal to 0 this is valid. Let us see at x equal to L. So psi of x at x equal to L, this should be a sine kappa L. This should be equal to 0. At x equal to L, psi of x should be equal to 0. So in that case, what should be the kappa L value? So kappa L will be n pi, because at n pi, sin n pi is 0. So n takes values 1, 2, 3, sin 180, sin 360, all these are 0. So kappa L is equal to n pi. So this is the condition that it satisfies the boundary condition. So this is our correct solution. So psi of x is equal to a sine kappa x is our correct wave function for the electron to move in the particle, that box, in one dimension box. Now if you see what is kappa is equal to n pi by L, and kappa is equal to square root of 2 me by h cut. From this, if you write the energy for n values, so En is equal to h cut square kappa square by 2m L square. So this is what we are going to get precisely. So, or if you change to this value, we are substituting kappa is n pi by L. So E is equal to n square pi square h cut square by 2m L square, so n square. So this is what is energy of the particle. So this we call it as energy of the particle or eigenenergy. So the eigenenergy or eigenvalue of this particle in a box or potential well is n square pi square h cut square by 2ml square. So far this is the energy of this particle which is moving here. Now let us discuss the wave function for this. So we know the wave function is psi of x is equal to a sine kappa x. So if you take that equation, let me just erase the boundary condition here and take the equations. So what is that? Psi of x is equal to, now let us see what is the eigenfunction. So eigenfunction for this particle is psi of x is equal to a sine kappa x. Now that we know kappa value, so a sine, you can say, you can substitute kappa is equal to, this is kappa x, so n pi by L into x. This is psi of x for us, the wave function for that. Now what is the a value, amplitude of this wave? So for that we will do probability density function. So we will take minus infinity to plus infinity mod psi square dx. So you are searching the particle between x equal to minus infinity to plus infinity. For this case, what is the lower limit? It will be 0 and the upper limit will be L. So if you search the particle between these two limits, definitely it has to be there. That means it should be equal to 1 because particle is there in the box. So what is the integration of this 0 to L? What is the complex conjugative of this a into a square? So which is a constant sine square n pi by L into x into dx. This should be equal to 1. So if you simplify this, I am going to write this a square 0 to L 1 minus cos 2 n pi by L into x dx equal to 1 by 2. So I am going to integrate this. So if I integrate this, I will get one term as dx. So integration of dx is x. So you will get a square by 2 into x, upper limit is L, my lower limit is 0 and that will be equal to 1. If I integrate this cos value, it will become sine. So sine 2 n pi by L into L by 2 n pi. But if you apply limits, you will get L cancel, sine 2 pi will become 0. So, and if you apply sine 0 is also 0. So that term you will get as 0. So, or it will vanish. So ultimately what you will get is A value is equal to square root of 2 by L. So this is the amplitude of the wave that is moving inside the box. So A value is root 2 by L. So we have eigen energy. Now what is the eigen function? So the eigen function is we can take psi of x is equal to root 2 by L sine n pi by L into x. So this is our eigen function. So this is eigenvalue and this is eigen function. So far we have seen eigen energies, eigenvalues of particle in a box and eigen function. Now what will be the probability of this particle to be there in that box where it will be more available? For that we have to take mod psi n square. So mod psi n square will be something like 2 by L sine square n pi by L into x. So this is the probability of finding that particle inside the box. Right. So this is the particle in a box. Let us understand these three equations, eigenvalues, eigenfunctions and probability density function of this particle, how it will look inside this box. So if you take the same box, and let me redraw the box at least here. So we have this box x0 xl and it is infinitely long, right? Now if you take sorry, if you take the energy levels, so if you take first n equal to 1 you will get E1, which is pi square h cut square by 2 ml square. So here h cut is h by 2 pi. So you can write h square by 8 ml square also. What will be n equal to 2? That is E2. E2 value will be 2 square of this, that is 4 E1. So on. E3 will be 9 E1. So on. So the energies are quantized. The energy levels are not continuous, they are quantized. Based on the energy level, they will be there. Suppose if you take n equal to 1 and draw psi of x, and take n equal to 2 and draw psi 2 of x, psi 1 of x, n equal to 3, psi 3 of x. So what is happening here? You take this equation, sine 0 is 0. If you put x equal to L and n equal to 1 in this equation, so then LL cancels, so sine 180, so that is also 0. If you take L by 2, so L by 2 LL cancels, n is 1, so pi by 2 sine 90 is 1, so it will have root 2 by L. So the height of this is root 2 by L. Similarly, you can take L by 4, 3L by 4, various values from x equal to 0 to L and connect the points. So you will get some points here, some point here. Then if you connect that, then you will get a sine wave because it's a sine function. So then if you go to n equal to 2 and do the same thing, so you will be having a wave which is like this. At x equal to L by 2, it will be 0. And if you go to n equal to 3 and draw this, you will have something like this. So based on the energy E1, E2, E3, this particle will have the wave function which is shown like this. Similarly, if you take probability density function and draw this, where the particle will be available mostly. So the particle will be available mostly, that we can see. Now this is mod psi1 of x whole square. Similarly, mod psi2 of x whole square, mod psi3 of x whole square. So this is for n equal to 1, n equal to 2, n equal to 3 for energy E1, E2, E3. So if you see this, you can take this equation and you will get here 0, because here x equal to 0, sine 0, x equal to L cancels, you will get sine n equal to 1, so sine 180, so it is 0. But if you take L by 2, then you will have pi by 2, so you will get the height of this is 2 by L. And you take L by 4 and 3L by 4, you will get some points here. But what is the change that you see from wave function and probability density function? Here you have square. So the values will increase rapidly and then decrease rapidly. So you will get some shape like this. Then if you go and draw this for n equal to 2, energy level 2, so how it will be? So this will be like here. But here, now it is square. So the negative will also be positive. So you will have same height here and then. Similarly, if you go to here, so what it tells, basically we have to understand it here is with energy E1, the particle that you are searching for inside box is most probably available at the center of the box. But if it has energy 2, you cannot find there. It is not there. The probability of finding that particle is 0. So the most probability of finding here at E equal to 2 is at L by 2 or 3L by 4. So this is how the particle is moving inside one-dimensional box. I hope you have understood this concept. We can extend this concept for three-dimensional box and further understand the density of states. So thank you for paying attention and listening. Thank you.